Welcome to day 2 of trigonometric substitution. I think that this topic is sufficiently tricky that it's worth just taking a second look and doing some more complicated examples. So first, remember what substitutions that you have to use. If your integral involves a squared minus u squared, you let u equal a sine of theta. And don't forget that your du is a cosine theta, d theta. Like I said before, this is the most common thing for you to forget. So if you get an integral that's really funky, make sure you didn't miss that. If your integrand involves a root of a squared plus u squared, use the substitution a tan of theta. In that case, du is a secant squared theta, d theta. And then finally, this is the least common one, but it probably will show up on like a take-home quiz. If you have u squared minus a squared, use u equal to a secant of theta. And then your du will be a secant theta tan theta d theta. Now the first thing we're going to do with this is we're going to use these trigonometric substitutions to find the integrals of these two random things I showed you on the very, very first day, and you maybe didn't know the formulas. So 1 over a squared plus x squared. You can prove this formula using substitution, like a regular normal substitution. It's a little bit tricky. Now another way to do it is to use these trig substitutions. So with this one, we have a squared plus x squared. I know there's no root sign, but it still works. We're going to use x equals a tan theta. So x equals a tangent of theta. And then don't forget dx. dx is equal to a secant squared theta d theta. Okay, and here we go. We have the integral of a secant squared theta d theta over a squared plus a squared tangent of theta. Oh, tangent squared theta. Excuse me. Whoops, that was a bad almost boo-boo. Okay, now factor out the a squared in the denominator, and we'll have a over a squared times secant squared of theta, d theta, over 1 plus tangent squared of theta. Okay, a over a squared is 1 over a. Everyone should know that. And 1 plus tangent squared is just secant squared. So what you really have there is secant squared over secant squared. So secant squared theta divided by secant squared theta. No, this is not a trick. That is 1. So that's 1 over a. The antiderivative of 1 d theta is just theta. So 1 over a times theta plus c. And go back to your substitution, no triangle here, we just have theta, so x over a equals tan theta, right? So theta is actually equal to inverse tangent of x over a. So this is another way to show that the antiderivative of 1 over a squared plus x squared is 1 over a arctan, or tan inverse of x over a plus c. And now that you've seen that formula, hopefully 2 ways, you're totally welcome to just use it. And it will apply whenever you have 1 over a number squared plus x squared and no root sign. So for example here, same idea, that a is equal to 3. Notice that a is actually the square root of that because the formula had a squared. So you can think, well, that 9 is 3 squared. So this is the same thing as 1 over 3 tan inverse of x over 3. Now let's do the same thing for the formula that I told you was sine inverse of x over a. So this is the first basic substitution. You let x equal a sine of theta, and dx will equal a cosine theta, d theta. Okay, so this becomes the integral of a cosine theta d theta all over the root of a squared minus a squared sine squared of theta. Now factor out that a squared, so a cosine theta d theta over root a squared times 1 minus sine squared theta. And that a squared, when you root it, becomes just a, which cancels with the other a in the numerator, so those a's are actually gone. So you have cosine of theta d theta over, well, 1 minus sine squared theta is just cosine squared theta, so look at that, the cosines cancel too. And once again, we have the integral of 1 d theta. And if the last one seemed like a trick, this one should really make you feel like you've been tricked, but you haven't. The antiderivative of 1 is just theta plus c. We have to find what theta is. And so since x equals a sine theta, x over a equals sine theta, and theta is sine inverse of x over a. So this is sine inverse of x over a plus c. So that's one reason, or one place that you can sort of derive those formulas from, is using this method. Now using this one, so same idea, a here is going to be the square root of 16, or 4. And so this antiderivative is sine inverse of x over 4. If you don't remember that and you get stuck, you can always do the whole trig substitution with x equals 4 sine theta. It's just you're going to end up with an integral of 1 d theta at the end, just like in the previous example. So if you run into a formula that is like one of those, you can just say what the antiderivative is. All right, now this one's tricky in a couple ways, so here we go. Oh goodness. So the first thing to notice is that we have 16 minus the quantity 3x squared dx. So we are going to start by letting 3x equal 4 sine of theta. And the reason we let equal 4 sine theta is so when we square that, we get 16. And then so 3 dx equals 4 cosine of theta d theta. And solving that for dx, because dx is all we have, dx will equal 4/3 cosine theta d theta. So when I replace my x's by cosines and sines, I'm going to put that 4/3 way out in the front already. So 4/3 integral root 16 minus 16 sine squared theta times cosine theta d theta. Don't forget the 4/3 is out here. Okay, now with that radical, first factor out that 16, so 16 times 1 minus sine squared of theta. And so the 1 minus sine squared makes cosine squared, which roots to cosine. And the root 16 becomes 4. 4 times the 4 in the numerator of the other fraction is 16. So 16/3 integral cosine squared of theta d theta. And here we have to use the half angle identities. So cosine squared of theta is 1/2 times 1 plus cosine of 2 theta. And in this instance, taking things back to x is going to be a little bit tricky. That's the part that's a little bit messy here. So 16 thirds times 1/2, or half of 16 thirds is 8 thirds. The antiderivative of 1 is theta. The antiderivative of cosine of 2 theta is 1/2 sine of 2 theta, positive, plus c. Now, the thing that's tricky is when you go to try to change back some stuff, you have 3x over 4 equals sine of theta. And you should know that doubling the angle doesn't necessarily like double the results. You can't say that sine of 2 theta is twice this. It doesn't work, it's not that easy. So what you have to do is use another trig identity, and I apologize, this is one of the ones you do have to know. Sine of 2 theta is the same thing as 2 sine theta cosine theta. So I promise that there are about 6 identities that you have to know, that being one of them, the Pythagorean being 3, and 2 more being the half angle ones like we just used right here. But this allows you to take a sine and make it into a sine times a cosine where the angles are just theta, not twice theta. So it's tricky, there's a lot of trig here. So 8 thirds times theta. Notice the 2 and the 1/2 cancel. So we have plus sine theta times cosine of theta plus c. And now if you look at a right triangle, this is your theta. So sine is opposite over hypotenuse. So the adjacent side is 16 minus 9x squared. And let's just plug everything in. Also, theta will equal arc sine of 3x over 4. So we have our final answer is 8 thirds sine inverse of 3x over 4 plus, now sine of theta is 3x over 4. Cosine of theta is adjacent over hypotenuse, so root 16 minus 9x squared over 4 plus c. And let's both multiply some stuff and let's distribute some stuff. So we have 8 thirds sine inverse 3x over 4 plus, now notice that this 3 will cancel when it multiplies by that 3. This 8 will cancel with one of those 4s, so that's 8 over 4, actually will be 8 over 16, so it'll just be a 2 in the denominator. So plus x root 16 minus 9x squared over 2 plus c. So there is your antiderivative. Wowza. All right, another one this one's kind of like, first you do a trig substitution and then you combine it with a regular substitution, which makes it a little bit fun. Fun's a little sarcastic there. So we'll let u equal sine theta, 1 sine theta, so just sine theta. Du is cosine theta d theta. All right, so this becomes the integral of root 1 minus sine squared theta over sine to the 4th theta times cosine of theta d theta. Now in that numerator, that 1 minus sine squared inside in the radical becomes cosine squared, which roots to cosine, which multiplied by the other cosine makes cosine squared. So cosine squared theta over sine to the 4th theta. Okay, and you can't do a u sub for sine because then your du would just be singular cosine, not 2 of them. Don't do half-angle identities when there's stuff in the denominator. Oh man, that gets so gross. I don't even think it works. So, cosine over sine is cotangent, and 1 over sine is cosecant. So the best way to take this one is to mess with it and make it into cotangents and cosecants. That's the best way I got. So if you have something else that's better, let me know, but this is what I have. So make this into cosine squared theta over sine squared theta times 1 over sine squared theta. Pattern recognition, that's all this is. So we have the integral cosine over sine is cotangent. 1 over sine is cosecant. Okay, and now at this step we're going to do a, well, I made a silly. I shouldn't have said u equals sine theta. I should have said x equals sine theta. And I should have said that dx equals cosine theta d theta. Whoops. Okay, now I'm going to make a u substitution. So u, to think whose derivative. So it's the derivative of cotangent cosecant squared, or it's the derivative of cosecant cotangent squared. And it is the case that the derivative of cotangent is negative cosecant squared theta d theta. Though that negative we can totally handle. So this becomes negative the integral of u squared du. So easy u sub, negative 1/3 u to the third plus c. So next input what u is. So we'll have negative 1/3 cotangent of theta to the third power plus c. And then your original substitution said that, let's look at it, x equaled sine theta. So x over 1 equals sine of theta. So in your right triangle, okay, so the opposite side is x, the hypotenuse is 1, the adjacent side is 1 minus x squared. So tangent is opposite over adjacent. Cotangent will be adjacent over opposite. So we have negative 1/3, adjacent being root 1 minus x squared, opposite being x, that whole quantity cubed, plus c. Bada boomba, there we go. Which, if you want to, could also be expressed as follows. You could write this as negative 1 minus x squared to the 3/2 over 3x cubed plus c. Same thing. Either answer is good. Alright, so in this next example, let's deal with one that's not just a simple x, but something sort of else. So here we have e to the 2x, and the thing that you have to observe is that e to the 2x is actually e to the x squared. So we have the integral of e to the x root 9 minus e to the x squared dx. So we can start this off, I think, by making a u sub, letting u equal e to the x, du will equal e to the x dx. And that makes this into the integral of the root 9 minus u squared du. Woo! And that's not so bad then. It will take a little bit of work, but it's not awful. Now, you let u equal 3 sine theta, and du is 3 cosine theta d theta. So this becomes the integral of the square root 9 minus 9 sine squared theta times 3 cosine of theta d theta. And it's awfully similar to the example that we had that was root 16 minus 9x squared. It's pretty similar. So take that 3 from the cosine theta out. 3 integral root 9 times the quantity, 1 minus sine squared of theta times cosine theta d theta. And if you can do this faster, spectacular. That 9 roots to 3, multiplies by the other 3, making a 9. And this 1 minus sine squared theta becomes cosine squared theta, which roots to cosine, multiplies by the other one, making it cosine squared. And here we are again in half angle city. So 9/2 integral 1 plus cosine of 2 theta. So anti-differentiate, and that's 9/2 times theta plus 1/2 sine of 2 theta. And because both variations are, the half-angled identities for both cosine and sine both involve cosine, as in what you get right here is always a cosine, you're always going to have to use the identity that sine of 2 theta is 2 sine theta cosine theta. Okay, so plug that all in, and our semi-final answer, penultimate, is 9/2 theta plus sine theta cosine theta plus c. All right, now we have to go back and substitute. So we have u is 3 sine theta, so u over 3 equals sine of theta. So in our triangle, if that's our theta, sine is opposite over hypotenuse, making the adjacent side 9 minus u squared. Okay, and theta will equal just inverse sine of u over 3. So we have 9/2 times sine inverse u over 3 plus sine of theta is u over 3. Cosine of theta will be the adjacent side, which is root 9 minus u squared, also over 3, plus c. Let's do our last step all in one. Let's distribute the 9/2 and plug back in what u is. So 9/2 sine inverse e to the x over 3 plus e to the x root 9 minus e to the 2x. Remember, e to the x squared is e to the 2x, all over 2 plus c. And the reason that this is a 2 in that second term that's not the c right there is because 9/2 multiplies by this thing, which has a denominator of 9. Canceling the 9s, just leaving the 2's. Now, a more tricky version, another sort of special application of this, is in certain integrals where you can complete the square, you can also do this similar kind of substitution business. So here we go. So first you've got to remember how to complete the square, and it's probably been an awfully long time for some of you. So here's how this works. We have x squared plus 6x, and that plus 5 I'm just going to scooch over for a moment. Now I want to add a number to this 6x, just a regular constant, so that when I factor x squared plus 6x plus this magic number, I get x plus or minus something squared. And the way you find that number is you take half of 6 and you square it. So you add 9. And then this x squared plus 6x plus 9 factors into x plus 3, the quantity squared. That's why it's called completing the square. You add in a number, which makes that expression into something squared. You complete it. And because you can't just add 9 without compensating, that's totally not like preserving equality, nor is it fair, and math is fair. Not life, math is fair. So if you added 9, you have to also take away 9 so that you've effectively added 0 and changed nothing. So that becomes x minus 3 squared minus 4. And to check this completing the square step, what you could do is multiply x minus 3 by itself. So do x plus 3 times x plus 3, and then take away the 4, and you should get x squared plus 6x plus 5. If you didn't, you made a mistake. And I can even verify in my head right now that that actually is right. You get x squared plus 6x plus 9 minus 4 makes x squared plus 6x plus 5. So here's why that's helpful. That makes this into the integral of x over x plus 3, the quantity squared, minus 4. And kind of like in the previous example where we made a u substitution for e to the x, here we're going to make a u substitution for x plus 3. So u is x plus 3, du is dx. Notice that that x in the numerator, x is equal to u minus 3. So that's kind of like all pre-processing. There's the complete the square. Here's the substitution. Oh my goodness. It's tedious, probably a homework question, not a quiz question. You get the integral of u minus 3 over the root of u squared minus 4 du. These integration techniques get really tricky when you combine them with other techniques. Now here's the next thing to observe. You can break this into two integrals as follows. You can make it into u over the root of u squared minus 4 du minus 3 times the integral of 1 over root u squared minus 4 du. So that's kind of like adding fractions in reverse. You add fractions by getting a common denominator and adding the numerators. You unadd fractions by taking the numerators and spreading them out all over the same denominator. Now I'm going to call these integral number 1, integral number 2. I'm going to evaluate each of them in turn in a different color. So this first one I'm going to call integral number 1. Now with integral number 1, you can work that out just using a regular old substitution. I've already used u. I'm running out of letters. I'm going to use w. So I can let w equal u squared minus 4. dw is 2u du. So half dw is u du. So number 1 is equal to 1/2 the integral of w to the negative 1/2 dw, which is the same thing as 1/2 times 2 root w plus some constant c, or square root of u squared minus 4 plus c. And remember that u was x plus 3, so this is the square root of x plus 3, the quantity squared, minus 4 plus some constant c. Or you could say, oh, that junk all squares out to x squared plus 6x plus 5. So there's the first one. Now number 2, that's the second one. Number 2 is going to involve a trig sub. I know, it just couldn't be nice enough, could it? So with that trig sub, you're going to let u equal secant of theta. du is secant theta tan theta d theta. Oh, and I'm a little bit wrong. U should be 2 secant of theta, and du is 2 secant theta tan theta. So for number 2, ignoring the 3 for now, because we'll just add that in later, we have that that's equal to the integral of 2 secant theta tan theta d theta over the root of 4 secant squared theta minus 4. So that becomes the integral of 2 secant theta tan theta d theta all over the root of 4 times secant squared theta minus 1. So secant squared theta minus 1 is tangent squared. The square root of this 4 is 2. All we end up with is the integral of secant theta. Like I said, it happens a lot. So that gives us ln absolute value, secant theta plus tan theta, plus another c. And you know that u over 2 equals secant theta, so make your little triangle. Okay, so secant is reciprocal cosine. Cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent, making the other side u squared minus 4. So that's ln absolute value. Secant of theta is just u over 2. Tangent of theta is root u squared minus 4 over 2 plus c. Yowza. Okay, now from here, our original integral, oh my goodness. And I guess we could go ahead and plug back in what u was, right? You could say that u is x plus 3. So this is ln of the absolute value of x plus 3 over 2 plus the root of x squared plus 6x plus 5 over 2. We had a previous example where the whole over 2's kind of factor out and absorb into the plus c's. You could also do that here. So your final answer is equal to integral number 1, so root x squared plus 6x plus 5 minus 3 ln absolute value x plus 3 plus the root x squared plus 6x plus 5. I just chose to take out those over 2's sort of in my head because I know that they could go away and it just saves me writing a fraction. So there's your final answer. If you leave the over 2's there, I'll know that you're right. I won't count you wrong. I'm just saying that they can go away. The main reason to go over the previous example is just to go over completing the square, because it turns out that that one is just super tricky because of the fact that it's involving a secant, but this completing the square is easier, just the completing the square part is harder. So the integral is easier, the completing the square part is trickier. So here's how we should start. Take that negative x squared plus 2x and factor out the negative. So make it negative the quantity x squared minus 2x. And then think about what number to add inside the parentheses. You take half of negative 2 and square it, so that's 1. But because of the negative outside the parentheses, you've actually added negative 1, so to compensate you have to add positive 1. So that completes to positive 1 minus the quantity x minus 1 squared. And if you want to verify that, expand that expression out, and you're going to get negative x squared plus 2x. I totally promise. Believe me. So your original integral now becomes the integral of 1 over the root of 1 minus x minus 1, the quantity squared dx. And these substitutions are much easier when you're able to do them with sines and cosines. And this one's actually even easier than that. If you make a u substitution and let u equal x minus 1, notice that du is just dx, and this integral becomes the integral of 1 over the root 1 minus u squared du, which you know is just arc sine, or inverse sine, same thing, inverse sine of u plus c, or arc sine of x minus 1 plus c. And the last example I would like to discuss is an indefinite integral. Now, technically speaking, you know how I said that you can do some of these as a tricky substitution? This is actually one of those cases. I just would like to show you the other way because I'd like you to be aware of how the substitution works. And in case that it is impossible to sort of use the tricky substitution way. So if you want to do it that way, just to verify you can, you totally can try it, but here's the way we're going to do it with the trig subs. So for this instance, you let x equal 3 tangent of theta. dx will equal 3 secant squared of theta d theta. And you have to change your bounds. So here's the different thing. That 0 goes in for the x, not the theta. So 0 equals 3 tan theta. That happens at the angle of theta equals 0. And if you plug in 3 equals 3 tan theta. And that implies that 1 equals tan theta. Well, that implies that theta is pi quarters. That's the angle at which sine and cosine are equal, and therefore tangent is 1. So sub all your stuff in, including your bounds. So you have the integral from 0 to pi quarters. In the numerator, you're going to cube x. You're going to have 27 tangent cubed of theta times 3 secant squared theta d theta. And in the denominator, we have the square root of 9 tangent squared theta plus 9. And by now you should be pretty good at these simplifications. I'm going to skip a few steps. Pull that 27 out, integrate from 0 to pi quarters. Let's just talk it through. In this denominator, this 9 plus tangent squared of theta plus 9, the 9 factors out, giving you tangent squared theta plus 1, which becomes a secant squared theta, which roots to singular secant, canceling one of these guys and that 3. So in your numerator, what you have left is tangent cubed theta times just secant theta d theta. And from here, we're going to actually have to do another substitution. We're going to do a trig substitution. But the nice thing with substitutions is definite integrals, so you don't have to go back to the original variables at all. So it won't work to let u equal tangent, because tangent's derivative is secant squared. So that option's out. It might work to let u equal secant as our end goal. And then du will need to be secant theta tan theta. Okay. And we're also going to change our bounds, so let's just do that before we forget how to do it. I'm going to change the bounds, but then leave them off until we change the tangents into secants. So if theta is equal to 0, this implies that u is equal to 1. And if theta equals pi quarters, this implies that u is equal to 1 over root 2 over 2, which is square root 2. So let's talk about how to break up that tangent. So we have the integral from 0 to pi quarters. We need to sub for secant. So we're going to make that into tangent squared theta times secant theta tan theta d theta. So we've saved one tangent. And now since tangent is squared, we can change that into secant squared theta minus 1. So 0 to pi quarters, secant squared theta minus 1 times secant theta tan theta d theta. And now let's make our substitution. So we have 27. Remember, our bounds change to 1 to root 2. And we'll just have u squared minus 1 du. Lovely. So that will be 27 times 1/3 u to the third minus u, evaluated from 1 to root 2. And it gets a bit tricky. So if you do root 2 cubed, that is 3 root 2's multiplied together. 2 of those root 2's multiplied together just make 2. So 27 times 2 square roots of 2 over 3 minus square root of 2 minus 27 times 1/3 minus 1. Yo, algebra. So 27 divided by that 3 is going to make 9. So that makes 18 root 2's minus 27 root 2's. And then we'll have minus 9 plus 27 for a final answer of 18 minus 9 square roots of 2. And that is all for trigonometric substitutions. Good luck on that web assignment.